Hello everyone, I'm Sinat, and so today I'm going to provide you a quick demonstrations of assignment project. So we are we are going to build a model to predict electrical energy output from a full predictor variable, including temperature, pressure, humidities, and vacuum, right? So if you look at this data, this is the labels, outcomes, and these are the predictor variables, right? So clearly it's why machine learning, and it is a regression task. So I'm going to explore different models of machine learning, different algorithm, different machine learning algorithm, and find out which one that is suitable and which one provide the best model. There's so many of them, but today for this assignment, I'm going to pick only 3, including regression, decision trees, and random forest. So for some of you who are familiar with machine learning, first we need to load some module like Panda, NumPy, Matplotlib, Seebones, because all these packets can do all the calculation, can read a CSV file like Panda, can read a file like CSVs, and NumPy can do all sort of a number, anything related to number, and this can do a plotting. So I first load the data, the CCPP data, and you can have a quick look. See, this is the output, electricity output, and this is humidity, which is predictor variable, pressure, vacuums, and temperature, right? And we can also look at the first 5 row by doing head using a cpp.head command. So you can see all this output and info command, looking at informations of the column, and also use describe command to look at summary statistic if you are interested to see what is the means of each variable. So let's say the temperature, the mean is 19, the standard deviation, and all the percentile 25, 50, 75 percentile, minimum, maximum as well. What I want to do first, probably it's different from what other people do. I like to split the data first before I do anything. Why I like to do it first? Because I want to blank myself. I don't want to look at the data too much, because if you look at, you go through it, you play around with it, you probably induce bias because your brain is very sensitive to it. So we just set aside the test set and just play around with training set. So we don't want to look at test set. And to do this, we can use scikit-learn, train test split, right? And you can just write this command, train set. So I just allocate 20% for test set. So you can do like 30% as well, but 20% is okay. And random state 42, just make sure that we split the same data every time. So for random state. So this one is just want to look at the distributions of each variable. You can see like the variable AT, the distributions of temperature with phi somewhere less than 50, 10 degree, somewhere around 200 observations have fallen this. So you see like a scatter of this distribution using histogram, and you observe this with other like vacuums and RH, AP, and PE as well. So we run I run a pair plot to see is there a relationship between predictor variables and the outcome. Let's say a PE variable. If you look at AT have a very strong negative relationship with energy output. Vacuums also, and AP sort of have a bit of relationship as well. You can see a trend. RH also, you can see it. They look like they have relationship, but it's a bit scattered. So by having a quick look, I can see like all the four variables sort of consider as predictors of energy output, right? You can look at one by one by doing a SNS joint plot, looking at the relationship between ATs and temperature and energy output, right? You can do this as well one by one if you like. And here is the distributions of electric energy output. You see the histogram. They sort of spread out as well because the predictor variable is different, so it looks a bit spread out. Or you can do a heat map, but it's just the same thing. It's just different interpretation. I'm not going to explain this. So what I do next is with train set, I want to drop PE variables, so I get only predictor variables. And the label, which is a PE, I just keep a PE. So we set aside predictors and outcome, right? If you look at predictor variable like AT, V, AP, RH, they have different scale. Like AP, the scale is somewhere more than 1,000. And AT, the temperature is somewhere like 8, 11, 20. So they have different scale. And if you don't do a scaling and you leave this, put all this unscaled data into machine learning algorithm, the outcome probably dominated by the one that have a large scale, right? AP. So to be fair, to find out which one is the best contributor of the outcomes, we need to scale the data, so they all in the same scale, they all fair, right? And to do a scaling, you can load all these module like standard scaler, like we do a standardization, and use all this file line to transform the predictor variable, so they all scale. And all this command as well to complete the scaling process, right? So because I'm given only 5 minutes, I can't explain everything in greater detail. But after you scale all the feature, we can start doing a linear regression model. So we can use scikit-learn and fit a linear regression model by adding a predictor variable and label into there, right? And we can play with a regression, do just a 5-column prediction. You can see they're sort of doing good. 448, 475. There's this sort of linear regression is sort of okay for me to predict. And if you look at root mean square error, which is the metric used to evaluate the model, the root mean square error is 4.5, which is not really large. But can I say this is the best model? I can't say it. Let's try decision tree regression. So you load all this, the module, and fit the regression tree. But something weird is that the root mean square error, which is a 0, suggesting that they are perfect fit, right? And decision trees is very good at capturing a nonlinear relationship. So sometimes they just overfit. And to verify this, I use a k-fold cross-validation to perform some cross-validation. So I use a 10-fold cross-validation. So I split the data into 10-fold and run a model 10 times. And if you look at the score, the score 4.3, 4.5, 4.7, right? So it's small. It's just that decision tree is not, it's not a good model, and they just like overfit the data. So we can't use this model to generalize, but it's not a good model, decision tree. So I'm gonna skip this one. So from what I did here is, the decision tree just overfit, and linear regression did better than decision tree, right? So let's try a random forest. So I feed a random forest and compute a root mean square error at 1.2, which is smaller than a linear regression. Linear regression is 4.5, so suggesting that a random forest fit the data better than a linear regression. And we can run a cross validation with looking at a root mean square error. It's somewhere for around, if you do a cross validation, it's somewhere around 3, 3, and 3. And if you look at cross validations of the decision tree, they're higher than random forest. So, if we compare the three models, random forest is doing better than a linear regression and decision tree. So the conclusion is random forest is the best model among the three model fit. I also went through a grid search, so it's like we want to try to optimize what a predictor variable that can be a good predictor for the energies output. I'm gonna just skip this. If you want to explore it, you can do a grid search, but I want to jump to evaluation, right? So here I evaluate the model, which is a random forest, using a test set, right? And do a root mean square. It's again 3.1, which is lower than a random, lower than decision trees, and which is smaller. I can say just smaller, better than linear regressions and decision tree. And I also can compute the 95% confidence interval as well of this, which is not really huge. So 2 to 3 is not really far. So the model is, the random forest is a good model to predict energies outputs, and I'm gonna use this to as the final model of my my data. Right. So this is the end of my demonstrations of the project, and I know it's quick because it's only 5 minutes, but I did a lot. And if you have any questions, just send me a question. Thank you so much. Cool.